Hello everyone, today in this video we'll be discussing the third module of DSA, which is related to the continuation of the linked list which we had started in the module 2, and here we will be learning about trees as well. Okay, so make sure you hit the like button, subscribe to my channel for more videos like this, and if you watch this video till the end you can easily score more than 80% marks. Without wasting any more time, let's get started. So the first topic is the linked list. Okay, so before that, let's revise what was there in the previous module. It's about the sparse matrices. So sparse matrix is a matrix which has majority elements as 0. Okay, so if you consider this example, count the number of zeros, it will be more than half, right? Total number are 16 elements and the number of zeros are 12 here, right? So the majority are zeros, that is called as sparse matrix. So what is the advantage of this is that we need not represent the zero matrices here, just represent the non-zero elements, and rest of them are obviously zero. We can even get to know that, right? So only we have to represent the six matrix or seven numbers here. So that is why we use the sparse matrix in a different kind of representation. So here what we'll be doing is we'll be using a header node. Okay, so in this header node we'll be having next here, we'll be having a down here, we'll be having right here. Okay, this is the header node, and header node is for the row I and also for the column I. For each row and column there will be one header node. Okay, and for each non-zero element the node consists of the following structure. So for each nodes, okay, we'll be having the nodes for this one, this one, this one, this and this one. Okay, so the non-zero elements will be having the node, and the node will be having the following values. Row value will be there, which column it is present, and what is the value, the data of it. And the down means in the next row, which is the non-zero element, it's pointing to that. And right means in the same row, which is the next non-zero element, it's pointing to that. Okay, if there is no such element, it will point to itself. Okay, like that, or else it will point to the head. Okay, so this is how the head and the non-zero element node is represented. So let's consider an example here. So as you can see in the sparse matrix here, we have the zeros and the non-zero element wherever it is present. Like for example, here in the 11 it is present in the first row, right, and 22 is present in the second row. So here we'll be doing the same thing. As you can see, how many non-zero elements are there? There are 5 non-zero elements. And how many rows are there? There are 4 rows and 4 columns. Okay, 4x4, it is 4x4 matrix, and there are 5 non-zero elements. So here in the starting part you can see header has 4, 4 and 5. 4 is the number of rows, 4 is the number of columns, and 5 is the number of non-zero elements. And after that we are making the means the connections like this. The first non-zero element, as you can see here in the first row and second column, it is 11, right? So 11 is the first row and second column. Okay, so first row, this is the first row, and the second column is this one, right? So here the 11's the node is made, and in the similar way 22's node is made here. And also in the 22, as you can see, there is written as 0 3 22, right? So 0 is the row number and 3 is the column number and 22 is the value. And from the down it is having an attachment with the header and as well as in the previous node. Like there is one row like this and there is one row like this, right? So that is what it is given. The next non-zero element down it is attached to, and since there is no more elements present in the right side, it is getting pointed to header here. Okay, it is pointed to here. This node is pointing to the header in the left side. So like that we will be representing the sparse matrix using linked list. Okay, so moving on to the second topic, which is the doubly linked list. So the main disadvantage of the singly linked list is that we can only move in one direction. Okay, but if you want to move in the opposite direction, that will be more beneficial. So we can use doubly linked list for that. So in the doubly linked list, we will be having two link part here, left link and right link. Okay, so this is how the doubly linked list will be represented. And in the end, there will be a null here, and in this end, there will be a null here. Okay, so the declarations of the structure will be as follows: struct node, and inside the struct node we will have L link, which is known as left link. Here we'll be having the in data, and here we'll be having the R link, which is the right link. We'll type the struct node as D node, means double-ended node. Okay. And what is the function? Now let's discuss the function. Function to insert a new double-ended node after the node pointed by star PTR. Okay, so let's discuss this in detail. Okay, so here what we are trying to do is we are inserting a node after a node pointed by star PTR. Okay, so let's make an example nodes here. Okay, so this is one node, and this is pointing to this node here. Okay, and this is pointing to this node. Okay, and this is pointing here and this is pointing to nothing. Now if we have been given a question that we have to insert our D node, okay, D node we have to insert in after pointed by PTR. So suppose that PTR is pointing here, and if we want to insert a new node, how will that be accomplished? So to do that, what we need to do is we need to add a new node. Suppose that this is the new D node, and what we will do, we'll point this pointer here, and the back pointer will be pointed to this one, and we'll be pointing this pointer to here, and this pointer will be pointed to this one. So in this way we'll be adding one new node here. For that, what are the necessary conditions and the codes we need to write? Okay, so let's discuss the codes one by one. So in the code part, what you have to do is first take the next and the previous value. Okay, so here next is equal to ptr r link. This is ptr's r link. Ptr's r link is this one. So r link is pointing to this one, right? So this will be next. Okay, next will be pointing here. Next, what you are doing, ptr r link is equal to new node. Ptr's r link will be pointed to new node. So ptr's r link is here, this will be pointed to new node. So this connection is made here. Okay, done. Next, new nodes L link will be ptr. New nodes L link will be ptr. So this will be pointed here. ptr is this one, right? ptr is pointing to here. Next, what we need to do, new nodes r link is equal to next. Next is pointed here. New nodes r link is pointed to next, and then next L link will be pointed to this one. Next L link is pointed to new node. Next L link is pointed to this node. So what happened? This became a part of the list. Okay, after ptr, this node is inserted successfully. So this is how we use the function to insert a new d node after a ptr node. Okay. Next is function to delete a node pointed by the header. Okay, so a node which is pointed by the header, that we have to delete. Okay, so let's take an example. So this is a header here. Okay, and the header is pointing to a node here, and that node we have to delete. Okay, and this also further points to some other nodes. Okay, so pointed by header is here. Okay, so we have to delete this node. So how we can do that? So to do that, what we are doing, previous is equal to nodes L link. Okay, nodes L link, the header is the this is head. Okay, let me make it clear. This is the head, and then we have to delete the node which is present here. Okay, this is node is to be deleted. Okay, now what we are doing, previous is equal to nodes L link. Nodes L link, what is the nodes L link? It is head, right? So this is the nodes L link, that will be marked as previous. Okay, and previous R link is equal to, also next is equal to nodes R link. Nodes R link is this, so this will be next. Okay, this will be next. Now this node is to be deleted, right? So what we'll do next, prefs R link is equal to next. Prefs R link, what is prefs R link? Prefs R link is equal to this. This is getting pointed to where? It is getting pointed to next. So this will be made a connection here. We'll make a connection here. Okay, we will make a connection to next here. Okay, after that, what is the next thing? Next is equal to, next L link is equal to previous. Okay, so next L link is equal to previous. This is previous, it will get pointed here. So what happened, the link part between the next and the previous is made, and node is not anymore needed. Okay, so what we will do, free cur, it's not cur, actually it is free node. Okay, not cur. Okay, so fill free node, so this will be deleted here, and the connection will be made between this and this, the previous and the current. Next node will be made a connection, and the node is successfully deleted. This is how the function works for deleting the node pointed by header. Okay, so that was about the doubly linked list. Moving to the second half of the module, which is the trees. Okay, so what do you mean by a tree? Tree is also a type of the linked list where we will be having different kinds of trees. Okay, so tree is a finite set of one or more nodes such that there is a special node called root, and the remaining nodes are distributed into many groups, that's called subtrees of the root. So let's take an example and understand it, what it actually means. Okay, so here consider the given tree below. This is called as a tree. Okay, you'll be having one node here, and that will be pointed to many other nodes here. Okay, so this will be pointing to B, C, and D, and further B will be pointing this and this. So this type of representation is called as a tree, and each of these is a node, like how we discussed, right? The left part is there, right part is there, like that. Only here left part and middle part and right part, three pointers are there. Okay, so this is also a tree, and the levels will be there. This is the first level, this is second level, this is third and fourth level. Okay, so some concepts are present here. The degree of node, what do you mean by degree of node? The number of subtrees of a node is called the degree of node. So this degree is 3 because there are 3 subtrees here. This degree is 2 because there are 2 subtrees here. This degree is 1 because 1 subtree is here. This degree is 1 subtree. This degree is 3. J's degree is 3. G's degree is 1. F degree is 0. There are no subtrees present. E's degree is also 0. There are no subtrees present. So that is called degree of the node. What is the degree of a tree? The maximum degree of the nodes present. Which is the maximum degree present here? 3. Because here also 3. There is no more degree than 3. So the degree of the tree is 3. Okay. Left or terminal nodes. Okay, leaf or terminal nodes. What is the leaf node? Leaf node is the ending node which does not have any more subtrees. This is a leaf, this is a leaf, this is a leaf. These three are also leaves. Okay, Moving on, we have the non-terminal nodes. Non-terminal is the ones which are except that leaf nodes. This is leaf node, this is leaf node, this is leaf node, this is leaf node. Except that all are non-terminal. This is non-terminal, 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 and so on. Okay. Non also called as internal nodes, and the leaf nodes is also called as external nodes. Okay. Moving on, we have siblings, children of the same nodes. Okay. Sibling means the E and F are siblings, and K, L, and M are siblings. G and J are siblings. B, C, and D are siblings, and so on. Okay. The children of the same parent. Okay. G and J are not siblings. Okay. So B, C, and D are siblings because it's coming from the same parent A. Okay. So like that. That is called as siblings. Ancestors are all the nodes from root to that point. Okay. So if I talk about the ancestor of F, who is the ancestor of F? B and A. Both are the ancestor of F. Ancestor of I, G, C, A. Ancestor of L, J, D, A, like that. Ancestor of J, D, A. Ancestor of C, A. Okay, you got my point. That is called as the ancestors. Next is level of nodes. Means how many levels are there? I just discussed here, right? How many levels are there here? 4 levels are there. So this is level 1, this is level 2, this is level 3, this is level 4. That is called as level of the nodes. And height or the depth is how much maximum it's gone below. The maximum level. That is called as the height or the depth of the tree. Now there are different types of trees. The most important one is the binary tree. Let's have a look at what is a binary tree. Binary tree can have at most 2 child nodes. Okay, at most 2. More than 2 child nodes cannot be possible. This is a binary tree. This is also a binary tree. This is also a binary tree. But this is not a binary tree because it has 3 child. That is not a binary tree. Okay, so properties of binary tree, there are 2 lemmas, very important question from exam point of view. Let's discuss them. Maximum number of nodes. Okay, so the maximum number of nodes on level I of a binary tree is 2 power I minus 1, where I is greater or equal to 1. Okay, let's start the proof. The proof is by induction on I. Induction, first we'll take induction base. The root is the only node on the level I is equal to 1. See, in the root will be starting 1 and the level will be I 1 here. Okay, and hence the maximum number of nodes according to this formula will be 2 power I minus 1, which is 2 power 1 minus 1, 2 power 0, which is equal to 1. So is the value true? The number of nodes is 1 only in level I is equal to 1 by using this formula. Okay, induction hypothesis. Let I be arbitrary point positive integer greater than 1. Means let I be any level like 2, 3, 4, any level it may be. Assume that maximum number of nodes on level I minus 1 is equal to 2 of 2 power I minus 2. Let's consider that in level I minus 1 the number of nodes are I minus 2. Okay, why it is I minus 2? Because here in the question it is given, if level is I, it will be I minus 1. If level is I minus 1, it will be 2 power I minus 1 minus 1, which is I minus 2. Okay, then the induction step. The maximum number of nodes on level I minus 1 is I minus 2 by induction hypothesis. Okay, induction hypothesis we are considering. Since each node in a binary tree has a maximum degree of 2, the maximum degree how much can be? 2 nodes can be there. It's a binary tree. So maximum degree can be 2 here. The maximum number of nodes on level I is 2 times the maximum number of nodes on level I minus 1. So there is 2 levels here. The maximum number of nodes here will be 2 times the maximum number of nodes here. Why? Because 1 will produce 2 here, right? So that will be multiplying here. 2 times I minus 2. In level I minus 1, it was I minus means I minus 2 here. This is the maximum number of nodes. So see, this is I minus 1 level, this is I level. Okay, here what is the maximum number of nodes? 2 power I minus 2, the upper one. So the down one will be 2, right? So down one will be 2 times the number which is up. The down one will be 2 times the number which is up here. So 2 times the number which is present here. So we'll multiply 2 into I minus 2, which is equal to 2 power I minus 1. That is only the proof which we wanted here. Because the degree is 2, it will be 2 power I minus 1. Second lemma is the maximum number of nodes in a binary tree of depth k is 2 power k minus 1. So maximum number of nodes, if there is a depth k, like this it's a tree and the depth k is there. Okay, k is the level. Then the maximum number of nodes is 2 power k minus 1. And that's the same formula which we are using, which we derived. Instead of I, we are taking k here. Okay, that's the another way to represent it. The second lemma is relation between the number of leaf nodes and the degree 2 nodes. Okay, number of leaf nodes means leaf nodes have the degree 0, right? The last node which is in the tree, that is called as the leaf node, and degree is equal to 0. The degree 2 nodes will be having 2 childs, so the degree of this is 2, like that. Okay, so for any non-empty binary tree, T if n0 is the number of nodes, leaf nodes with degree 0, n2 is the number of nodes with degree 2, then the relationship is given by the number of leaf nodes will be equal to number of nodes with degree 2 plus 1. Number of leaf nodes is equal to number of nodes with degree 2 plus 1. Let's prove that. Okay, so here let n1 be the number of nodes with degree 1 and n be the number of total nodes. If total nodes are there, n how it can be represented? Total number of nodes equals all the nodes with degree 0 plus all the nodes with degree 1 plus all the nodes with degree 2. This is the total sum, right? Let's take that equation 1. If we count the number of branches in a binary tree, we see that every node except the root node has a branch leading to it. Okay, so if we consider a normal tree here, except the root node, from for root node there is no branch coming. This for this there is a branch coming, for this also there is a branch coming, right? Like that for all the subsequent node there is a branch coming inside from the top, but for the root there is no branch coming from the top. So if b is the number of branches, then total number of nodes will be b plus 1. Why? Because plus 1, why we are doing, to consider the root node. The total number of branches equal to the total number of nodes, and root node does not have a branch, so we are adding 1. That will give us total number of nodes here. That is the equation 2. So remember these equations, we will be using them to substitute in the further procedure. So here all branches stem out from a node of degree 1 or degree 2. Okay, so all the branches stem out only if the degree is 1 or 2, right? If there is a leaf node here, there is no branch coming out of it. In leaf node there will be no branch. If it is of a degree is equal to 1, there will be one branch. If it is a degree 2, there will be two branches, right? Two branches will be there. So all the branches stem out from a node of degree 1 or 2. So number of nodes if it is degree 1 plus 2 times number of nodes if it is degree 2. The total number of branches will be, if it is node is having degree 1, one branch is coming. If it is having 2, two branches are coming, right? So we can write total number of n1 plus 2 times n2. That will give us the total number of branches. Now the sum of branches that stem out from a node is equal to the number of branches inserted in the node. That is equal to out degree is equal to in degree, right? Because obviously if one branch comes out, it will be pointed to some other branch in node, right? See, it is not possible that there will be a branch command and there will not be any node here. Obviously there will be node here. So a branch coming out from here is equal to a branch going in from there. Okay, so wherever a branch comes out, it will obviously go inside the branch, so the number will be equal, number of out is equal to number of in. Okay, so substituting the equation 3 in equation 2. So what is equation 3? This is the equation 3, and in equation 2 if we substitute, instead of b we'll be substituting this one, n1 plus 2 and 2 will be putting here. Okay, so it will become n1 plus 2 and 2 plus 1. Okay, so this will be the n value. Now subtract equation 4 from equation 1. What was equation 1? Equation 4 is n is equal to n1 plus 2 and 2 plus 1. Equation 1 was n is equal to n0 plus n1 plus n2. If we subtract both of them, the LHS will become 0, and when you subtract this one, n1 and n2 will get cancelled, and n0 will be left with 1 n1, right? N1 is get cancelled here, and 2 n1 is there, so it will become 1 n1, and 1 will be also present. We'll be taking to the we'll be keeping it here only, and here minus n0 will be there, we'll be taking it here, it will become plus n0. Okay, you can do it yourself to verify. So you'll get this final equation, which is the n0 is equal to n2 plus 1, which is number of leaf nodes is equal to number of nodes with degree 2 plus 1. Okay, so this is two very important lemmas from an exam point of view. Make sure you learn it very well. Okay, moving on, we have the types of binary tree. There are different types of binary trees. Okay, so it is a full binary tree will be having all the nodes as 2. Every node will be having a child. Okay, 2 child will be there on every node. Okay, so that is called as full binary tree. Complete binary tree will also have all the nodes as 2 child except the last level. It can be either full or not full. That is complete binary tree. Extended binary tree, all the nodes should have 0 or 2 children. So as you can see, every node has either 0 children, this has 0 children, this has 2 children, this has 2 children, this has 0, this has 2 children, here it is 0 and 0, here it is 0, this is having 2, and so on. This is called as extended binary tree. Next we have the strict binary tree, same as extended 2 tree. Okay, so this is also the same as a strictly binary tree only, the extended binary tree, but there is some slight differences which we need not go into. Okay, almost complete binary tree will also have the same thing, except that two conditions are there. A node n at level less than d minus 1 has 2 child nodes. So this is level D, this is D minus 1. D means depth. Okay, depth minus 1 level, it should have all the 2 nodes should be present. That is one condition. For any node n in the tree with a right descendant at level D, n must have a left child, and every left descendant of n either has a left child or has a 2 children. Okay, so this is very complicated, not going to the details of it. So there is some rule that the right descendant should not have more than 2 nodes, or each left descendant should have a number of nodes, and also, so you get my point, right? So almost complete binary tree is a complete binary tree, but with slight differences. Okay. Moving on, we have the next one, which is the binary tree representation. So since you got to know about the binary trees, let's see how it is represented using a linked list. Okay, so here we have two links, right? Because each will be having at most two child nodes. So there will be a left part, there will be a right part. Okay, so struct node in data to store the data part, struct node star left, struct node star right, and type def struct node will be taking as tree node here. Okay, so it will be like this: data part will be here, and there will be a left part and the right part here, and the data will be pointing to left node and the right node here. Okay, so let's take an example. If this is the tree given, A will be having connection with B and C, B will be at the left, C will be at the right, and C does not have anything, so there will be nulls present here, and B has a left and right T and E, so it will be presented as follows. And this is how you represent the binary tree, okay, using linked list. Now, traversal. What is traversal? Binary tree traversal means that visiting each and every node in the tree, and there are three ways to do it. Okay, visiting each node means I'll start from here, I'll go here, I'll go here, I'll go here, and go here, like that. Okay, I'm going to each node. Okay, so that is called as traversal. There is different ways to do that. First I will do this, then I'll come here, and then I'll go here, like this. Or I will go this and this first, then I'll come here, and then I'll go there. So there are rules for it. Okay, three ways. Let's discuss. Very easy and yet very important questions from exam point of view. First one is in order traversal. Remember the keyword L N R. L means left, R means right, N means node. Let's discuss what it means. Void in order tree node star ptr. So there is a tree whose root node is pointed by star ptr. I'm taking that as the parameter, and inside that, if I'm taking if ptr, if ptr is there, then only I should do something. If it is not there, I cannot traverse only. If ptr is nothing, so where I will traverse? I can't traverse, right? So I'm checking if ptr is there or not. Then what? Very simple for this code. Write in order ptr left link, because this is lnr, right? Ptr left link. In the last you write in order ptr right link, and after that in between you write printf percentage d ptr data. So here what is actually happening? According to this code, first we are visiting the left part, then we are printing the node value, then we are printing the left right part. Okay, so here what's happening? I am starting from the root node here. Okay, first I will go to the left. What is the left of a? B. Again, every point I should do lnr. Okay, when I am staying here I should do lnr. Okay, let me make it more clear. So see here, at each point I have to complete LNR. Okay, LNR should be completed. L means LNR, it should start from L. L means visit the left node. I visited the left node. Now in the left node also I should do LNR. Okay, again there is a left part here, so I have to first complete L here. LNR. Again in this point I have to do LNR. In left, is there anything? No, it is not. So this is completed. N. N means what is present here that I have to print. Okay, so I'll be printing D here. Okay, after that this is also completed. Then I will go to the R. Is there any right node here? No, it's not. So that is also completed. Once L and R of one node is completed, go back where it came from. When you go back here, L is completed. Okay, you have completed the left part. Then N is present. N means print the N value, which is B here inside this. So N is also completed. Then go to the right part. Is there any right part? Yes, it is. So I'm going here. Now again I will do L and R. Okay, now here left part is there? No. Node is there? Print the node E. R is there? No, it's not there. So this is done. After this is done, I'll go back where I came from. I'll go to B. From B also, R part is completed. I'll do it like this. Then B part is completed. And to B where I came from. From A I came. So in the A I will be again doing the same thing. So the A's left part is all explored. So it will be cut here. N means print A value, and then cut this one. And is there any right part for A? Yes, it is. So go to the right part and then check for this one, L and R. Is there any left part for C? Yes, there is. F. So check the LNR for here. Left part is there? No. N is there? Yes. So print it. And R is there? No. Don't print. Go back here to C. In C, L part is completed. N, print C here. And then go to the right. G is present here. So uh, the n is printed. Okay, I have to go here, right part, right? So L and R is present here, left part is done, and there is no left part. N, I'll print G here, and right part is not there. I'll not do anything. I'll go back here. Right part is explored for C, so I'll cut this one. I'll go back here. Right part is explored for A. Once this right part and left part all are explored for the root node, that means you have traversed the whole node in this order. This order, if we do, it is called as in order. First we are considering L, then R, N, then we are considering R. Okay, this is called as in order. So in means in between. Okay, node is in between. That is called as in order. Left and right will be always like this. N will be changing. For in, N will be in between, and in next is the pre-order. In pre-order, N will be first, and then okay. So this is the code. First you have to print F PTR start data, which is N, and then we have to go to the left, which is L, and then we have to go to the right, which is R. Okay, so let's do the same thing for here. I'll come here and I will write NLR. Now node I will print first. N is first, right? So I have to print A here, and then after N is done, what is next? L. I have to go here, and here in B I will be again doing NLR. So what is N? B. Just print it. Okay, then cut this, and L is present here. Go to here, and then again NLR. Okay, you get the point, right? N here, D. I'll print D, and this is cut. L. Is there any L part? No, it is not. R. Is there any R part? No, it is not. Again go back where you came from. Here left part is completed. Now go to the right part. In right part it is E. Here also put NLR. N, print the node. E. L is there? No. R is there? No. Go back where you came from. B, right part is explored. Go to A. In A, left part is explored. Now next is right part. Go to the right and do the same thing here. NLR. So I'll be writing it quickly here. It will be C, F, and G. Okay, like that. If you follow the same procedure, you'll get this answer. This is the pre-order traversal. Pre means previous. Okay, so N will be previously. Okay, like that. Last is the one which is the post order. Same thing. L, R, N. First you have to do left, then right, then N. So here it will be printf means post order left, post order right, then print data N. Okay, so here it will be, once I go here, it will be L, R, N. I have to explore the L first. So I'll come here. Here also L, R, N. Here I have to explore the L first. So here also I'll go L, R, N. Here is any L is there? No, it's not there. R is there? No, R is not there. N is there? Yes, I'll print D. I'll come back here. Left part is explored. R part is there. In the R part, I'll go here. E is there. L, R, N, I will write. Left part is there for E. No. R, right part is there for E. No. N is there. Yes. Print E. Again, go back here. L, R, N is done for E. Go back here in B. In B, right part is completed. Print B value. Like that, we'll keep on going. Then this is also completed. I'll come here, and it is L. L is done. Next is the R. Right part. Come here. Here also write L, R, N. Okay. Then from here LRN, right, left part. From here go to the left part. F. In F, LRN. Is F having a left part? No. Is F having a right part? No. Node, print F. F will be printed here. Okay, then again go back here. L will is completed, and from here next is R. Go to the R. Again write LRN. D has G has the left or right part? No, it does not have. N is there? Yes. Print N, and then go back here. Right is explored. N is there. Print C, and go back here. N is completed, and here right part is also explored. When you come from C to A, right part is explored. N is print here. Print A value. This is called as post order traversal. Okay, you have to follow this procedure. Post means last, right? Post afterwards. So N will be at there at the last. This is the code words you have to remember, and very important question from exam point of view. You can get for the traversals, you can get for the code part, you can get for the evaluation also. We'll be discussing the traversal using an actual example. Okay, same thing you have to do. Okay, let's do it together. Okay, you also have to write it, and or you can just watch the video. Just keep doing in your mind. Okay, and let's see if we both reach the same answer. Okay, so this is an example here. You have to do pre-order. What is the code for pre-order? NLR. So let's write here NLR. NLR. Okay, now node left right. Node means A should be printed first. It is done. Now left, I have to go to the left. In B, NLR, print B. Go to the left. NLR, NLR. Then again D, print D. Go to the left. NLR. Then again print G. Go to the left. Is there any left? No. Go to the right. Is there any right? No. Go back. L part is done. Right part is any there? No. Done. Go back. L part is done. R part is there? No. Go back. Here left part is done. Right part is there? Yes. Go to the right part. NLR. Here C, N you have to print first. Okay. After that, L part, L, N, L, R. Is there any means first you have to print N, right? So N will be printed E, and L, L you have to go here again, N, L, R. Okay, here is there a means you have to print first H, and left and right part it's not there, so it is done. And come here, L is done, R, the right part is here. Okay, so in the right part we'll print N, L, R again. So node I, left and right part is not there, go back here, right part is done, go back here, left part is done, right part what is there, F, so print F here, N, L, R, left and right part is not there, go back, R is not there, go back here, R is completed. So this is the pre-order traversal. Okay, in the same way we will be doing the in order and post order traversal as well. Okay, so in order LNR. Okay, so LNR. So now first go to the left. Here also LNR. Go to the left, LNR. Go to the left, LNR. Left part is there, no, completed. N, print G, and then R. Is any right part? No, go back. L part is completed. N, print D. After that R. Is any right part? No, go back. L part is done. N, print B. N part is done. R is there? No, go back. L part is done. N, print A. R, go to the right. L and R. Go to the left. L and R. Go to the left. L and R. Left is there? No. N, print H. R, no, it's not there. Done. Go back. L and R. Left part is done. N, print E. N, done. R, go to the right. L and R. Left, nothing is there. N, print I. R, it's not there. So I will be printed. Go back. R is done. Go back. L is done. N, print C. R, go to the right. L and R. Okay, and left part is there, right part is there, no, print N. F, go back. N, I have to print okay, N was done before going to right. Okay, so I have to do that. R part is done. I will go back here, and A also I had printed. Yeah, I have printed A, so right part is also done. Okay, so this is the answer you will be getting for in order traversal. Okay, moving on, we have the post order traversal. What is the post order code? LRN. Okay, let's take LRN. Left and right both should be explored, then only N should be printed. LRN, go to the left. LRN, go to the left. LRN, go to the left. Left and right is not there, print node G. Left is done, right is not there, print N, D. Left and right is not there, left is done, right is not there, print N. Left is done, right is there, so again here LRN, again LRN, left, LRN. Left and right is not there, node print H. Left is done, right is not, right is there, so LRN. Left and right is not there, N, I. Done, go back. Right is done, N, E. Done, go back. L is done, R is there, LRN. Left and right is not there, N, print node F. Go back. Right is done, N, print C. Done, go back. Right is done, now N, print A. This is the post order traversal. Okay, so that was about the traversals. Very important question from exam point of view. Using the traversals, a similar concept is there for expression tree. We'll be evaluating the tree. Okay, so let's have a look at this also. It contains operands and operators. Operands are the numbers, and the operators are plus, minus, divide, or multiply. Okay, so these are the operators. So we can represent the expressions. This is an expression. It can be represented as follows: a plus b into c. So I'll put plus here, and then a and into here, and b and c. So first b and c will be calculated, b into c, then a plus b into c will be taken. Okay, like that. So this also we can traverse using different ways. If we traverse using in order, we'll get a plus b into c. If we do it in a pre-order, we will get a into b c, a plus a into bc, and if we do post order, we'll get abc into plus. Okay, so based on our requirement, how we have set it, we have to traverse in the same way. Okay, now next is the evaluation of a expression tree. Very important question from exam point of view. How do we evaluate a tree? Start from the last nodes here. Okay, 6 is here, 2 is here. Divide. What is 6 divided by 2? 3. 3, 3, do plus 6, 2, 6, do multiply 12, 12, 4, do divide 3, the result is 3. Like that. Okay, you have to evaluate the expression of the tree. The last topic is a threaded binary tree. Okay, so threaded binary tree is also a binary tree where we will have thread. Now what is a thread? Okay, let's have a look. What is a thread? A binary tree that has more null links than the pointers, then these null can be replaced with special pointers called threads. What does thread do? Okay, so suppose that if ptr's left part is null, means leaf node, the last node will be the leaf node, the left and the right will be null here. So if it is null, replace it with in order predecessor of ptr. First, for the whole tree, calculate the in-order traversal and take the predecessor, means the previous node in the traversals sequence. What is the previous node of the PTR that you have to take and point the left part to it? Okay, confusing? I'll take an example and explain. Don't worry. So if it is PTR right is null, replace it with in order successor of PTR. That is two-way threading. In one-way threading, only the right is considered. It will be, if it is null, it will be replaced with in order successor, and PTR left remains unchanged. Okay. One-way threading will focus only on the right part. Two-way threading will focus on both left and right part. Okay. So here is an example. Okay. So you will be given like this, and you will be asked to calculate the threaded binary tree sparse. Okay. So what you have to do? Start from here. First, do the in order traversal. Okay, LNR. When you do LNR here, LNR, 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 LNR. Here you will print H. Then L is done. N. You will print D. LNR I. So H D I. Then you will print B E A F C G, like that. Okay. If you do in order traversal, you get the following. After you have got this one, find out the leaf nodes. That's the second step. Find out the leaf nodes. Which are the leaf nodes? Which either left or right part is null. E has left and right part null. H, I, F, G. All these have left and right part null. Note down here. After that, the third step is make the table like this. E, F, G, H, I. Whichever you have got here, write it in this way here in the rows. And the column write two things, predecessor and successor. Now, E's predecessor and successor will be what comes before E, that is E's predecessor. What comes after E is E's successor. Okay, so B is predecessor of E and A is successor of E. Same for F. What comes before F is A. A is the predecessor of F, and what comes after F is C. So C is the successor of F. Okay, in the same way you'll do for G also. G's predecessor is C. G's predecessor is C, but after G there is nothing, so we'll consider root node. Okay, what is root node? A. Just write root or A here. And for H, before H there is nothing, so that will be again root node. And successor is D. For I it is D and B. For I it is D and B. After you have done this much, you have to just make a threads. Okay, what do you mean by threads? Okay, let's take an example. What is meaning of threads? Thread means you will be making a point. Okay, so see, actually it will be like this. Okay, last node I am taking H. Okay, H will be like this. Since we are including threads also now, so threads will be like this. Okay, we'll be having thread here. Okay, the last two are for the left thread and this is for the right thread. Okay, if it has a thread, we'll be marking this as true. If it does not have a thread, we'll be marking it as false. Okay, these two things we'll be doing inside the last two. And this is the data part as usual, data, and this is the L link, and this is the R link. Okay, now in the last node, observe, in the last node, is there any left or right link? No. So here it will be null, here also it will be null. So when both are null, left thread will be possible, right thread will also be possible, so both will be set as true. Okay, so for H it will be like this. Okay, for H it will be like this. This is the data H and left node. Okay, since it is null, we will have a thread here, and right node is also null, so we'll have a thread here. So left thread should point to which? Let's see the example here. Here in H, the left should be pointing to root, so this will be taken and pointed to the root here. Okay, root means it will be for A. This is A and this is not null, so it will be false, and this is pointing to B, right? A's left part is B and A's right part is C, and this will also be false, so this will be pointed to A like this. And right part, what is H right part? D, so here D will be there, right? Here D is there, and D's left and right are H and I. Okay, so H and I are the D's left and right, and this will be false because left and right is there, and this part will be pointed to D here. Okay, this is how you do the means markings. Okay, and D is pointing to H, so D's H part will be like this. Okay, so let's do it for the whole diagram. Okay, all you have to do is take it like this, make the boxes and do. Okay, I'm just doing it for the circles here, you have to do it for the boxes like how I did here. Okay, in that way you have to make the points. Okay, I'll just do it directly here. So start from E. E's predecessor is B. Okay, E's predecessor is B. So take a left point and do it like this. E's successor is A. E's successor is A. Do it like this. Actually, you have to do it making the boxes, and the null part you have to make it here like how I did here. Okay, like that you have to do. F is AC. F is A and C. Next is G is C and root. G is C and root. Root will be here. H is root and D. H is root and D. Okay. And I is D and B. D and B. Got my point? Okay. So this is how you will be making the threaded binary tree. Okay. So since we used in order traversal, we'll also have to use the in order traversal only for making the threads. Okay. We have discussed about in order traversal. We have to use in order traversal only. So the code is as follows. Let's discuss quickly. So finding the in order successor. How do we find the in order successor of the node? Take thread node. In successor is the function. The thread node start tree. For the tree we are trying to find out the in order successor of tree. Okay, this node whichever it's pointing, we are trying to find out the successor of that. Take a temp node here. Tree is equal temp is equal to tree arrow right. The right part of tree will be in temp. Okay, what will temp have? Right part of tree. While if tree of right is nothing here, means it is having nothing, means this is tree, the right part is null. Okay, that case what we have to do, we have to find out the successor. In this case only find the successor. If it is not null, we need not find the successor. Okay, how we'll find the successor? While temp arrow left thread is equal to f. Temp is what? Tree's right part. Tree's right part. That is what? The temp. Now temp's left thread. Temp's left thread, if it is having f, we'll be checking if it is having f or not. If it is having f, do temp arrow left. We are going as left as possible. Okay, you need not understand like how it's actually working, because in order traversal we cannot intuitively see and understand. Okay, it's the formula they have created, and if you trace it we'll get to know, but there is no time for that. Okay, just have to understand. We are first taking temp here, tree arrow right. Tree arrow right is f, then we'll do temp arrow left thread is equal to f, and then temp is equal to temp arrow left. If you want to actually know how it is working and trace it by taking an example and knowing, but for now we'll be just going through it, what is the code doing. After that we'll be returning temp. So temp will have the leftmost part of the thread, which will be the successor of the tree. Okay, so that is how we find the successor. And to in order traversal of a threaded binary tree, normally how we do, take the tree here, use a for loop with no conditions here, and this for loop will run until we reach the end. Okay, thread node temp start tree, so temp will be a pointer of tree, and we'll find out the successor. After we find the successor, if it is true, means if it is having the successor as tree only, the successor itself, that means break, means only one node is there, and successor of one node is the same one, predecessor of the same node is same one only. So in that case we'll break, else we'll print temp arrow data. Then again we'll come here, we'll take the next temp successor of the next temp, and again we'll print successor of the next temp, print. So it will print the successors, and that will be the in order traversal. Okay, that's all for this video. If you found this video helpful, make sure you hit the like button, subscribe to my channel. That helps me make more videos like this. Thank you so much for watching. I'll see you in the next one.